remember, you can use V equals IR as long as it's for the same thing. So R and 2 combined, and it says they want the resistance of R1, R2, and the parallel connection. So you're going to use V equals IR each time. So if you want it for R1, then you're going to use that values. So you're going to say V for R1 is equal to I that flows through R1, and the resistance of R1 must always be the same. So we have V is 9. We have I is 1,5, and we can then work out R. Super easy. So you just have to stick in the values. Then they say, is the value of the resistance for the parallel combination in agreement with the theoretical value? So if you worked it out, it's probably going to be a little bit different. Yeah, so they're saying why. So that's a nice question. Why is it not the same? So if you is the value for the resistance R2 combined. Okay, so if you work, okay, now we need to work it out. What is this one going to be? So R1 is equal to 6, and then is it?
Yeah. R2 is 12.
No. Yeah, it is. Okay, and then R2 is equal to 12 ohms. So if they were in parallel with each other, what should it be? So the R parallel, so that would be 1 over 6 plus 1 over 12, and that gives you to the minus 1, and that gives you, I don't know, I don't feel like doing the maths. And then if you're doing this calculation using the values, then you would get here, you would, if we use these values R and 2 combined, the ammeter reading here is going to be 2, and the voltmeter reading is 8. But that's still, did you use this or did you use that to get the 4?
R1 and R2, the one that we worked out now.
Yeah.
The R1 and R2 we worked out using the ammeter
This.
A, ammeter B.
But then it is the same.
Yes.
Is this giving you 4?
Yes, that gives you 4.
And this gives you 4. So why do they say it's not the same?
That's voltmeter reading.
Oh, true. Okay, so why is the voltmeter reading not the same? So that's again why. What happens when you put it in parallel? Same argument again. If you add something in parallel, what do? Total resistance decreases, therefore total current goes up, therefore I times little r, well, there must be, otherwise the readings would be the same. I times little r will decrease because little r stays constant, therefore V external will decrease because EMF is constant. The same argument we used earlier, but write it out properly and use the right equations. Okay. So
Now,
can we
the
leave?
pair of readings is the first reading just R1 and then the second reading R1 and R2.
Wait, say again what you said?
It says here, the question says for each pair of readings.
Yeah.
So that's R1 and R2 separately.
So this will be the readings for R1 only. It says she connects R1 alone, then R2 alone, and then R1 and R2 in parallel. So this is for R1 alone, this is for R2 alone, and this is for them combined. So for each of these, I would be different. So that means V internal would be different for each of them. So that means that the external voltage would be different. And you can see it. They're all different. If they ask us now to calculate the internal resistance of the cell, can we do it?
Yes.
How? Actually, that's a good question.
Can you try find R total and I total? Then find the total.
We have the total.
And reduce it to minus the voltmeter.
What always stays the same? EMF and little r. So what you can do, you can say for this one, that was the only thing connected. So you can say that EMF for that first, when you only had R1 connected, EMF is equal to I little r plus I big R, right? Okay, so you know, you don't know what the EMF is, but you know that the current is 1,5 times little r plus 1,5, and you worked out the resistance, so you know it. What was it again? 2 for this one. Okay, so that would be equation number 1. Then you go and do it again for the second ones. And you do the same thing and you say EMF is equal to I little r plus I big R. EMF is constant, remember, so this EMF and this EMF is the same. So you can say that this is, we have the current is 10,3, oh, sorry, no, 0,86, 0,86 times by little r, which is also constant, so it's the same as that little r, plus 0,86 times by the big R that you calculated here, whatever it was. What was it for the second one? Now you've got a new market, equation number 2. But now you know that this EMF and this EMF is the same thing. So it's simultaneous equations.
But isn't the top one supposed to be 1,5 times 6?
Yeah.
Yeah.
I don't know. I asked you guys. I didn't do the math.
Because
The
the
first
4
one is
is in
6,
parallel.
is 6,
4 is in parallel.
This is
So it's supposed to be 6.
Okay. So now we've got two EMFs, so I know that these two EMFs are equal. So that means these two equations must be equal. So that means 1,5 little r plus 1,5 times 6 is equal to 0,86 little r plus 0,86 times 12. And little r is my only unknown, and you can go and solve it. Once you have it, you stick it back and you get the EMF. They like this simultaneous equation thing. Remember, what you must remember is that EMF is always constant and little r is always. Why are you frowning?
What was the
What was that?
Did we have the EMF? No, we didn't have it.
No, you've got two equations, two unknowns. So this could be also a higher order question in your test. Okay, number 9. Okay, so they're giving you a circuit. They tell you V1, reading is 10.8. If it's not on your circuit diagram, go and put it in there. It just helps you to see everything helps me to see everything on the diagram. They say the reading on V2 is 3 volts. V2 is 3 volts, so they've given us that. It looks a little bit as if it could be the battery. Just make sure that you don't think it's the battery. The EMF of the battery is 15. They didn't give us that. So the EMF of the battery is 15 volts. The reading on the ammeter is 1,2. They've given us that. If the reading of the battery is 15 volts and the resistance of R1 is 5 times of R2, R1 is 5 times of R2. So give it a think. Say that R2 is X, then what would R1 be? 5X. Make your life easy for yourself. You guys are good with X's. I've realized to stop fighting the battle to call it R. Just call it what you want. Call it R. X. Okay. Now, the numbering is a bit weird.
Yes,
I'm assuming they want the resistance of R3. Okay, so R3 is what they want here. Okay, so the first thing, for R3, always go and think, what works for R3? Write down everything that works for R3. So if I look at R3, can I use V equals IR? That's always your first thing to go to. Do I have V?
Yes.
Yes, I know it's 10,8. Do I have I?
It's not the total thing.
It is. It's the total current because it didn't split up here. The total current goes through R3. It splits up here, yes. But then it combines again there. So actually, yes, it is 1,2. Remember the first question will always be easy-ish. So it is 1,2 times R. So I didn't need any secret information. Everything was given to you. So R is just going to be 10,8 divided by 1,2, which is
9.
9 what?
9 ohms.
Ohms. So this is that one there. Sorry, they ask. They asked for R3.
Yes.
What about 9.1? Is 9.1 a question?
Mhm.
They said no. 9.1 is not a question. Yeah, calculate the resistance of R3. Then the total resistance of the circuit, including the battery. That should be total always. So again, they want the total resistance. So we can use V total is equal to I total times R total. They want this. Do I know what V total is? 15, because V total is always the EMF. Do I know what the total current is? Yes, it's 1,2. So again, no secret information. If you stick to V equals IR, your life becomes super easy. R total then is going to be 15 divided by 1,2, which gives you what?
12.5.
What?
Ohms. Now I get what you want.
Now they want the internal resistance of the battery. How am I going to get that?
And do not need to specify.
Again, there's so many ways. Yeah, tell me a way.
We need to get the external resistance.
We can get the external resistance. Okay, but how are we going to get that? We know that this voltage here is 3 volts. So we know that this voltmeter reading here is 3 volts. So what would the voltmeter reading here be?
3 volts.
Also 3 volts. So what is V external actually?
10,8 plus 3.
Thank you. 10,8 plus 3 volts is my V external. So that's going to give me 13,8. If I know that that is my V external, what could I do?
V internal.
I know what V internal is because V internal is just going to be the EMF minus that. So V internal is going to be 15 minus 13,5, which is
What?
1,5 is V internal.
13,2. That means 1,2. Because it's 13,8, not 5.
15
Oh, did I write down wrong? What?
It's 13,8, not 13,5.
Oh. Ay, ay, ay. 13,8. So this is going to be 15 minus 13,8, which is 1,2. So that's V internal. And once I have V internal, I can say V equals I times little r. I know that this is 1,2 is equal to I, which is 1,2. Little r, so r little r is 1. That's one method.
Hey, 1 ohm.
You could have done that other equation that I don't like so much, but it's there. So you could have used it and you could have said EMF equals I R plus R. We know the EMF is 15. We know the current is 1,2. Big R, we have calculated. Normally you don't have it, but this time, oh, actually no.
Yeah.
We don't have.
But couldn't you just say you have the V external? So couldn't we just work out the resistance of the external?
You could have worked out this one's current, and then its voltage, and then its resistance if you wanted to.
No, I was saying we already have V external and we have 1,2 ampere. So we want to get the total external resistance. Couldn't we just say 13,8?
You could have done that. Yeah.
And then
So I still think this is easier, the first way, method we did, but it doesn't matter. Yes, you can do that. You can say V external is equal to I external or external, as long as they're still the same. So we do have V external, yes, that's the 10,8 plus the 3. So that's the 13,8. So it's kind of all the same thing. I is still 1,2. And then you could have gotten R external.
gives you
11,5 ohms. And then we're going to stick that into there. So then we can say that this is 11,5 plus little r, and you should still get a little r of 1.
Yeah, I was gonna say because we got the total resistance.
Yes,
So couldn't you say 12,5 minus 11,5?
But that's this, back to this method again. Oh, or that. Yes, or that. Can you see how many methods there are? So many methods. That's what's nice about electricity. And then the last thing they want R1. Okay, now that becomes very easy because we've kind of worked it out a few times already. So we know what V is. You need to know what the current is that goes through each of them. If the current is 1.2, it's going to split up in a ratio, remember? 5 parts will go here, 1 part will go there. So you have to divide it by 6.
No, the top one gets 1, but the bottom one gets 0.2.
Okay, this one gets 1 and this one gets 0,2.
Isn't the other way around? Inverse ratio.
Yeah.
Oh yeah, it's inverse, yeah.
This one gets 1 and this one gets 0,2. And then you can use V equals IR again. Our magic equation. So you're going to say V is equal to I times R. 1 is what they're asking us for. So we're looking at V there is 3 is equal to the 0,2 times by R1. So R1 is 3 over 0,2. Is? What is it? 15 ohms. Okay. If they ask you about brightness, what are they talking about? Power, because you all know that. If you're connecting things in series, remember they're going to become dimmer. But if you're connecting them in parallel, they're going to stay the same. That's why in a house, all our lights don't go dimmer and dimmer the more you switch on things. So when you buy a light bulb, so if you get a question about wattage that's written on a light bulb, if they say, I'm buying a light bulb and in the shop it's labeled 220 volts, 50 watts. What it means is if you connect it to 220 volts in parallel, it will give you a wattage, a power of 50. But that's only if you connect it in parallel. Please remember that. If you're going to connect them in series, they're not going to give you 50 watts. They're going to give you less.
Which one makes them dimmer in series?
Series makes them dimmer. Okay, so just remember that as well. Anything else?
Now, why do the lights that are connected with the resistance in parallel for lights, why do those lights last longer? Right?
In parallel, because they don't necessarily last longer. They just shine the same brightness. Did someone say they last longer?
But
They will actually last longer in series when they're dimmer.
yeah, but they
Batteries
use
are
this.
not long when they parallel.
Now do also use now look at
Batteries, man. When they parallel.
You
No.
said something about that. Something last one minute.
One of them was long and parallel, man. That's what I remember.
I don't know why they would necessarily last longer. Let's do that. So if you are connecting them, so if you're looking at a parallel circuit, this is important though. If you have light bulbs in parallel, so they often ask you this, if they have different resistances. So let's say this has a resistance of 5 ohms, and this one has a resistance of 15 ohms. Okay, remember resistance stays constant. So if you now take those same light bulbs and you connect them in a circuit in series. So you take those same light bulbs and you put your 5 ohms here and you put your 15 ohms here. So they often ask you about brightness and use an equation to explain which one would be the brightest. So then you have to remember for all the explanations, always think what is constant. So if you're looking at a parallel circuit, what remains constant? The voltage. So when you're looking at, and power is brightness, so you're going to find your equation that has power and voltage in it. So you're going to say P equals V squared over R. But because this is constant, only if and only if V is constant, then I can say power is directly proportional to 1 over R. So if the resistance is higher, what's going to happen to the power? It's going to decrease. So which one will be the brightest?
Is that right? Also can last long because I said.
That's probably, yeah. So now which one will be the brightest? The one with a lower resistance. So the 5 ohm one in parallel will be the brightest. But now if I go to series, what remains constant in series? Current. So now you're going to use P equals I squared R. Oops. Now if you look here, it's I squared that remains constant. So if and only if I squared is constant, can I say that P is directly proportional to R? So now this time, the highest resistance will give me the higher power. So which one will be the brightest now? The 15 ohm. Because if you look at it here, voltage is energy. So each of them gets the same. So let's say there's no internal resistance, and this is a 10, 10, the EMF is 10 volts. That means this one gets 10 joules of energy for every coulomb, and this one gets 10 joules of energy for every coulomb. So they get the same energy. But where is it the easiest for the coulombs to go? A hurdle of 5 or a hurdle of 15? 5 is easier. So more of those coulombs with its 10 joules will go here. So this one will get 3 times as many coulombs with 10 joules, 10 joules, 10 joules, 10 joules. So this one will be higher because more goes there. But if you think about this one, yeah, the same coulombs go there. So the coulombs go, they give off some of their energy here, and they give off some of their energy here. But it's the same coulombs. So now you need to think, are they going to give off more energy to a 15 hurdle, or are they going to give off more energy to a 5 hurdle? 15. So this one gets more energy. Okay, so this one gets a higher voltage, but they get the same amount of coulombs. Make sense? Okay, I really can't think of anything else that could be in the test.
Oh yeah, how would we have to work on the price?
That's the
Crash course.
Do we need to know? I'm saying, will that
There could be one. I haven't looked at your test in detail yet. Yes, it could be. So if remember, cost is always ESCOM charges us in kilowatt hours. So that actually gives you a tells you what to do because it's kilowatts and it's hours. So when you're paying for each kilowatt that you're using and you're paying for the time that you are using it for. So this kilowatts is power. So they're giving you power. So you always have to, so cost is going to be equal to the kilowatts hours that you are using times by the money that you have to pay for each of them. So what you need to remember is that you're going to take each watt that they give you and change it. No, they will give it to you in watts. So whatever they give you in watts, you have to convert them into kilowatts. Whatever they give you days or hours or seconds or weeks, you have to convert it into hours. And then you times it by the money that it costs you per kilowatt hour, and that gives you your cost. You don't get this equation though. So you